Question 5. So in the figure 5.1, we have the aromatic hydrocarbon, cumene. And okay, let's start part A about this compound. Complete table 5.1 to show the number of sp2 and sp3 hybridized carbon that present in a molecule of cumene. Okay, so sp2 carbon, okay, the benzene ring, all the carbon actually they are sp2. So total 6 carbons here, 1, 2, 3, 4, 5, 6. So numbers of carbon sp2 is 6. sp3 they are this. Okay, all the carbon outside the benzene ring. So because it's all saturated, so they are all sp3 carbon. So 1, 2, 3, 3 only. Okay, this one easy. Okay, part B. Cumene can be synthesized via the alkylation reaction. So we use this halogenal alkane. Of course, this one we need to use the catalyst. So since it's bromine here, we need to use AlBr3. Okay, so this one we'll discuss later. And okay, after the alkylation, means this alkyl group is get into the benzene ring. So is obviously an electrophilic substitution. So you need to form the electrophile first, which helped by the catalyst. Okay, so which is this one. So the halogenal alkanes that used just now, okay, the bromines will form bonds with the catalyst, the AlBr3. So eventually the CBr bond will break here, and it will form the AlBr4 negative. And after this bond break, then it will form this carbocation. So the carbocation is like this, look like this one. Okay, so then the carbocation will use for the alkylation. So that's why this is the electrophile that used for the reaction. And we say that it's an electrophilic substitution because this electrophile is the one that substitutes the hydrogens in the benzene ring. Okay, part 2 is the catalyst. As I told you just now, we need to use the AlBr3. Okay, part 3 completes the figure 5.3 to show the mechanisms for the reactions of benzene with the carbocations that we mentioned just now. Very easy. This one you need to draw one arrow from the benzene ring, point to this carbocation. Must point to this carbon because the new bond will form between the benzene ring carbon with this carbon. Then if you form the intermediate, okay, remember to draw a curve with charge positive. Okay, so together with the alkyl groups and the hydrogens, and this intermediate is served 1 mark, and you need to show the CH bond break. Draw one arrow from the CH bond, point back to the ring. So eventually the hydrogens ion will released, right? So here, and these hydrocarbons will be formed, right? So this is a mechanism, very easy. Okay, so for these alkylations of benzene by 1-bromo propane, this one, it also produce this cumene as a major product. Okay, so this primary carbocation, CH3, CH2, CH2 positive, form in the first step is quickly rearranged to form the carbocations that we use for the mechanism just now. So suggest why in this case, explain your answer. This question is quite different. So you just need to compare the stability of the secondary carbocation and the primary. Okay, so for this primary carbocation, the CH3, CH2, CH2, this one, right? So because only one alkyl group bond to this to the carbocation, so it's less stable because it has lesser positive inductive effect. Whereas for this secondary carbocation, so this carbocation now is bond to two alkyl group, CH3, CH3, these two methyl group, and it has a greater positive inductive effect. So means it's going to be more stable. Means the charge positive here is actually lesser, more stable, right? So because this one is more stable, then it's going to form more. That's why this one rearranged to form this secondary carbocation. Okay, cumene oxidize in the air to form phenol, right? So and this propanol, and this is the equation for the reaction, right? So reaction 1, and the enthalpy is given negative 371 kilojoule per mole. For this part 1 is very easy. Based on the equation and the molar entropy given, so you need to calculate the delta S. So the center entropy change for the reaction 1. Okay, just remember, use the entropy of the products minus the total entropy of the reactant. So you just take the value from the table. Product is the phenol, so phenol with the propanol minus the entropy of the this cumene and oxygen. So eventually the delta S you get is negative 137 joule per Kelvin per mole. This one is very easy, simple calculation. After that, show that reaction 1 is feasible at 25 degrees C. Okay, 25 degrees C you need to convert to Kelvin. Okay, first you need to use this equation, the Gibbs equation. Delta G equal to delta H minus T delta S. Okay, when you want to use this equation, make sure you convert the units, the entropy from joule to kilojoule. So means the entropy here you need to divide by 1000. Okay, convert the joule to kilojoule. And the temperature, it must be Kelvin, 25 plus 273. So this is the part you must do. Then you can use the enthalpy together with this. So negative 371 minus this, you should get negative 330 kilojoule per mole. Since the delta G now is exo, then or negative, so reaction 1 is feasible at this temperature. Okay, part D. Figure 5.4 shows the two reactions of phenol. Okay, this one, phenol, it has reaction 2 and 3 here. For this reaction 2, the phenol react with bromine. So it will form this 2,4,6 tribromophenol. Okay, because phenol, the benzene ring is highly active, so it will react with the bromine easily without any catalyst. So it will form this tribromophenol. It's a white precipitate. How it reacts is something like this. This is just a general guide. Okay, so the phenol, because the benzene ring is quite active, the lone pair on oxygens get into the ring, activates the ring. Then it can easily react with the bromine and eventually form these products. And phenol also can react with the R and together with the sodium hydroxide to form this azo dye. You can see this azo link. So this is azo dye, and this part is from the phenol. So means this part must form the R. So the R that you need to suggest is the benzene diazonium ion. This one, the benzene ring with these two nitrogen. This nitrogen is charged positive. So the phenol, it will donates electrons to this nitrogen, okay, and eventually is formed this azo link. So now we know that the R is actually this benzene diazonium ion. And of course the reaction, this we call coupling reaction. It needs to use the sodium hydroxide for the reaction. Okay, so now part 1 is what I told you just now for reaction 2. Explain why these conditions are different from those of the bromination of the benzene. Okay, so because the normal bromination of benzene, you need to use the catalyst. So the bromine with the AlBr3. But the phenol no need the catalyst. It will just react with the bromine. So then you need to explain why. It's just only because of the lone pair on the oxygen. So I told you just now, the oxygens, okay, it has lone pair, it can delocalize into the ring. So when the lone pair get into the ring, okay, the benzene ring has more electron, means it's more active, so it can easily react with the electrophiles like bromine. So condition is just bromine water without any catalyst. And you just explain like what I told you. Lone pair of electrons on oxygen delocalize in benzene ring, and this will increase electron density in the ring, and it will let it be more able to attract electrophile. So the extra electron density activates the benzene ring and enable it to polarize the electrophile more compared to the ordinary benzene ring. Okay, part 2, draw the structure of the organic compound in Q. Organic compound Q in the figure 5.4. So this one already told you is a 2,4,6 tribromophenol after the reaction 2. And identify organic reagent R. I already told you just now. R is benzene diazonium ion. Okay, you just draw this. Name the functional group in reaction 3. So the functional group is okay, this one, the azo. This is azo link. Okay, part 5. The phenol will react with the nitric acid to produce a mixture of products or isomers. So identify the two isomers. This one is very easy. Phenol, if it's react with HNO3, so because phenol is the 2,4 directing, so means phenol is going to direct the substitution on the 2,4 position. So let's say this is first, so this is second, okay, third, fourth. So means always the phenol as an electron donating group, it will direct the electrophilic substitutions, okay, at the auto or para position or 2,4 position. It's the same thing, 2,4 or auto para. So means the isomers, it will be 2-nitrophenol or 4-nitrophenol, because the phenol is 2,4 directing. So the hydroxy group is electron donating here, so which is 2,4 directing. Therefore, we get these two products, 2-nitrophenol and 4-nitrophenol. Okay, that's all. Thank you.